Welcome everyone to the next video of the series of videos for Calculus 1. In this video, we are going to define limits, and then we are going to use tables and graphs to estimate the limit of a function. So in the last section, we talked about the average velocity and the instantaneous velocity, and then the relationship between them. And also we talked about the secant line and the tangent line. So let's go ahead and quickly recap what we did. So for example, this curve represents the function f of x. And then let's say we have a x equals a here. So, and then let's say this point here is a, whose coordinates are a comma f of a, and then let's say we have a x value b here, and then we have this point right here, which is, let's say, b, and the coordinates are b comma f of b. Now if we draw the tangent line passing through these 2 points, so let's say this is the tangent line AB, okay, going through these 2 points, then the slope of the tangent line AB is given by f of b minus f of a over b minus a. Now, if we move this point B, okay, so if we move this point B closer and closer to A, then we get this different tangent line. So for example, different secant line. So for example, if I move B over here, or this B value over here, then I get this secant line going through that point. Now, if I further move that B values, let's say over here, or point B over here, then I get another tangent line, sorry, secant line. And then if I keep moving that closer and closer, let's say I get it very, very close to A. So I move this B very close to A. And then I have the secant line here. So when I do that, okay, so when I keep moving point B closer and closer to A, what happens is the secant line AB approximates the tangent line at A. So we can say as we move point B very, very close. So let me put that here. So very, very close to A, point A, then the secant line AB approximates the tangent line at A. Or we can also say the slope of secant line AB approximates the slope of tangent line at A. So now this idea of very, very close, I say when we move B, point B very, very close to A, remember when we found the uh, instantaneous velocity, we used to take the distance between A and B very, very close when H approaches 0. So here, when that distance is very, very small, or when B is very, very close, okay, so then that secant line approximates the tangent line. So now here, the idea of saying that very, very close, okay, so the idea of very, very close, or that closeness, how close? Really close, very close, okay, so the idea of very, very close is what limit means, is limit. So that is the general idea of limit, okay? So we are going to define this mathematically, but now limit means when you move a point, or yeah, when you move one point very, very close to the other point, okay, on the graph, we'll be able to approximate the slope of the tangent line using those 2 points. So that idea of very, very close, or that idea of closeness is what limit means. So that's the general idea of limit. So let's do this more mathematically, okay? So here we have a function f of x equals x squared, and then we are going to see what happens to this function when x approaches 2. Okay, so when x is 2, let me write it here, and we are not talking about what happens at 2, so I'm not going to look at this value. Okay, so what I'm going to do now is I'm going to take numbers close to 2 from both left and right side. Okay, so if I move closer to 2 from left, so I can say, okay, so I can take x equals 1.9, and then I can go closer to 2 by taking x equals 1.99, and then I can keep going closer to 2 by taking the point 1.999. Similarly, I can come closer and closer to 2 from the right. So I can start at 2.1. Then I can move closer, which is 2.01. Then I keep moving closer, which is 2.001. So when we move, okay, closer and closer to 2 from both direction, from left and right, what happens to this function? So what we do now is we'll take these x values and plug them into our function and see what happens. So if you take 1.9 and put it here, so if you find f of 1.9, then that gives you 1.9 squared. Okay, so and this equals 3.61. So this is 3.61. So similarly, if you plug in 1.99, you'll get 3.9601. So if you plug in 1.999, you'll get 3.996, and then there are more numbers after that. Okay. So similarly, if we plug in 2.1 into our function, we'll get 4.41. If I plug in 2.01, I'll get 4.0401. And then if I plug in 2.001, I'll get 4.004001, and maybe more numbers after that. So now, what does this tell us? Okay, so when x approaches 2 from both the direction, we can clearly see that the function is approaching to a value of 4. So if you look from left, it's 3.996, which is very close to 4. And if you see that from the right, same thing, we have 4.004001, which is very close to 4. So now we can say that as x approaches to f of x approaches 4. Now, mathematically, what we can say is, mathematically, we can write, okay, so we can write limit of f of x as x approaches 2 equals 4. Or we can also say limit of x squared as x approaches 2 equals 4. This means when the independent variable x gets closer to 2, the function is getting closer to 4. Or when x is approaching to 2, the function is approaching to 4. So this idea is what limit, okay? So now in general, the idea of limit is what does a function do as the variable, the independent variable, approaches a given value. In this case, when the independent variable x approaches to 2, what does the function do? And we can say that the function approaches 4. So this idea, or this is what limit means. Now we have a definition of limit in the next slide. So now we will look at the preliminary definition of limit. More technical and formal definition we'll look at the end of this chapter, okay? But now we will see the preliminary definition or intuitive definition of limit. This helps us to understand the limit, okay? This is very general kind of very easy kind of definition. The one that we'll see at the end is more technical and a little bit challenging, but with this one, we'll really understand what limit means. Okay, so this is the formal definition. So we have a function f of x. Okay, so we have a function f of x which is defined for all x in an open interval containing a. So if you take an open interval, so let's say b comma c You have an open interval that contains a, so this interval contains a, so a is in that interval, b comma c. Okay, so we can say that so this is the function f of x. Then let's say a is somewhere here, this is a, and then we are taking some open interval. Okay, so a is in that interval. And what does the function do? The function is defined for all x in the open interval. So the function is defined everywhere on that open interval except possibly at a itself. That means at a, the function might be defined, might not be defined. It's okay if the function is not defined at a. So what we are, the concept here is we are really not worrying, or we don't really care about what happens at a. We just care about what happens when we approach very close to a. Okay, so the function is defined everywhere here. When we approach close to a, all the points near a, okay, the function is defined, but really at a, the function might be defined, might not be defined. We really don't care. Okay, now, if f of x is arbitrarily close to L, so if f of x is very, very close to L for all x sufficiently close but not equal to a, so this is very important here, okay? So it means when we approach to a, okay, when the x value approaches a, and the x value is not equal to a, we are just approaching, we are getting very, very close to a, okay? It's not a, but we are getting very, very close to a. Then the function is getting very, very close to some value, let's say, which is L. Okay, so as x approaches a, the function is approaching to L. Okay, so if that happens, then we say and we write, so limit f of x, okay, so limit of f of x as x approaches a equals L. And it's exactly similar to the example that we looked at earlier. Okay, so this is the definition of limit. So basically what we have to understand here is we have an open interval that contains a. The function is defined everywhere on that open interval except at a, it might be defined or might not be defined. So when x value or the independent variable approaches a from both directions, the function is approaching to a particular value L. So then if that happens, then we say limit of f of x as x approaches a equals L. So this is the preliminary definition of limit. So let's see some example which makes better sense of this definition, okay? So the first example here it says use the graph of f to determine the following values if possible, okay? So the first one, we are asked to find what is f of x at 0 or f of 0. That means what is the value of the function at x equals 0. So x equals 0 is right here. So we can see the value of the function is 2. So f of 0 equals 2. Now the next question is, what is the limit when x approaches 0? Okay, so what is the limit of f of x as x approaches 0? So that means 0 is right here, x equals 0 is right here. So when we approach to 0 from both the direction, where is the function going? So when we approach to 0 from right, the function is approaching to this value right here. And then when we approach to 0 from left, the function is approaching to this value right here, which is 2. That means the limit of f of x as x approaches 2 equals 2, okay? So in this case, the value of the function at 0 is same as the limit of the function as x approaches 0. We got the same value here, and that's not always true. Okay, so we could get a different limit and we could have a different value of the function, because remember, by the definition, we really don't care what happens at that a, okay? We are just looking at what happens to the function when x approaches a. So let's look at another one. So f of 1, that means the value of the function at x equals 1 is, so on the graph we have a hole, but if you look over here, the value of the function at x equals 1 is indicated right here, which is -5. So f of 1 equals -5. Now let's see what's the limit when x approaches 1. Okay, so what's the limit of that function when x approaches 1? So 1 is right here. So when x approaches 1, if you see, the function is approaching to this value right here from the left. Similarly, when x approaches 1 from the right, the value of the function is approaching to this value. So that means when x approaches 1, the function is approaching to -1. So in this case, the value of the function is not same as the limit. So and it's totally fine. So again, just remember that thing, okay? So we are not really looking at what happens at a, but we are looking at what happens to the function when x approaches a. And in this case, when x approaches 1, the function is approaching to a value of -1. But the value of the function at 1 is -5, okay? Now let's look at the third one here. So find f of 4. That means where's the value of the function at x equals 4? It's right here, which is 2. So the value of the function is 2. And what is the limit when x approaches 4? So when x approaches 4 from left and right, the function is approaching to this value right here, which is again 2. So in this case, the value of the function at 4 is same as the limit of the function as x approaches 4. Now here is another example. I want you to pause the video and try this example on your own, and then you can resume the video and check your work. So the first one, we are asked to find h of -2. That means what is the value of the function as x approach x is -2. Okay, so here is -2. The value of the function is 1. And then the limit when x approaches -2, what is the limit of the function? So when x approaches -2, the function is approaching to this value right here, so which is again 1. Now the second part of that question, it says find h of -3. So at x equals -3, what is the value of the function? We have a hole here, so the value of the function is right here, which is 5. Now what is the limit of the function as x approaches -3? So as x approaches -3, we see that the function is approaching to this point here, and the value of the function, I mean the y value here, is 0. So as x approaches -3, the function from the graph, you can see the function is approaching to this y value, which is 0. So this limit equals 0. Okay, now the next part of that question is find h of -4. So at x equals -4, the value of the function is again 1. And the limit is when x approaches -4, the graph, from the graph, we can see the function is approaching to this value right here, which is again 1. So I think you have a clear idea how to find limit from the graph. So now, so far in those two examples, we look at a function where the function is approaching to a particular value from both directions, but that's not always true, especially when we have piecewise defined function. When you approach to a x value from left and right, the function might not approach to the same point. Then what happens with our limit in that case? So in that case, what we are going to do is we are going to define limit from one side, okay? So the first one is right-sided limit, or we also call right-hand limit. So that means when x approaches a from the right, so this small positive sign here indicates that x is approaching to a from right, okay? It's not positive or negative number. That just indicates that we're approaching to a from the right. Then the limit of the function is L. So from when we are approaching to a from right, when x is approaching to a from right, where is the function going to? So that gives us the right hand limit. Similarly, when x is approaching to a from the left, and then we indicate that using this small negative sign here, that means we are the x is approaching to a from the left. In that case, wherever the function is approaching, that is the left hand limit of that function. So let's look at this graph here and then see what happens So let's see that definition here. Okay, so let's say if I say limit of f of x, okay, as x approaches -2 from the right. So that means here is -2. So when x approaches -2 from the right, so that is small positive means we are approaching to -2 from the right side of the -2, okay, from the right of -2. Then we clearly see that, so the function is approaching to this value right here, which is 1. Now, if we say, okay, so limit x approaches -2 from the left. So in this case, what we are doing is we are moving towards -2 from the left. So when we go to -2 from the left, the value of the function, or the function is approaching to this value. So this graph, so this is where you walk. So when you're walking on the x-axis, and then if your corresponding value on the y-axis is walking over this line, okay, on this line, and then this indicates that when we are approaching to -2 from the left, the function is approaching to this value here, which is 3. So f of x, that equals 3. So this means at -2, the left hand limit is 3, and then when x approaches -2 from the right, or the right sided limit, or the right hand limit, is 1. So that's what one sided, left side limit and right side limit means. Now, why is this important? We'll see that in the next graph here. Next slide. Now, for a function, okay, so f of x is a function, then for a limit when x approaches a of f of x to exist, we should have the left hand limit equal right hand limit. Then only we can say the limit exists. Or in another word, we can say that the function has to approach to the same value from both directions. Then only we say the limit exists as x approaches to that value. Okay, so the limit of f of x as x approaches a equals L if and only if the left hand limit equals right hand limit and equals to L. Otherwise, we say the limit does not exist. So let's see that from this example, okay? So let's look at this graph here. So if I take a point x, so if I'm taking, okay, so limit x approaches -3 from the right of f of x equals, so -3 is right here. So when we approach to -3 from the right, the function is approaching to this y value, which is 0. Now if I say limit x approaches -3 from the left side of f of x, so when we approach to -3 from the left side, again the function is approaching to that y value, which is 0. So in this case, the left hand limit is same as the right hand limit, or as x approaches -3 from left and right, the function is approaching to the same value, which is 0. So that means from here, we can say that limit as x approaches -3 of f of x equals 0, because left hand limit is same as right hand limit. But now if we take this another point here on that graph, so if we say limit x approaches -2 from the right of f of x equals, let's see, when x approaches -2 from the right, the function is approaching to, okay, so the function is approaching to this value, which is -1. Okay, so this is -1. And then when you say limit x approaches -2 from the left of f of x, so when we are approaching to -2 from the left, so when we go to -2 from the left, the function is approaching to this value here, which is 1. So in this case, the left hand limit is not same as right hand limit. Okay, so right hand limit is -1, left hand limit is 1. So that means the limit as x approaches -2, f of x does not exist, because the left hand limit is not same as right hand limit. So let's look at some examples here. So the first one, so let's use this graph. So this one, the first one says limit as x approaches 1 from the right of f of x equals what? So let's find this limit, okay? So when x approaches 1, so 1 is right here. So when x approaches 1 from the right, the function is approaching to this value, which looks like 1/2. Now, when x approaches 1 from the left, okay, so when x approaches 1 from the left, so when we go towards 1 from the left, the function is approaching to this value here, which is -4. So here the right hand limit is 1/2, left hand limit is -4. That means limit of h of x as x approaches 1 does not exist, because the left hand limit is not same as right hand limit. Similarly, let's look at the other one. So as x approaches 6 from the right, so when x approaches 6 from the right, so when we approach to 6 from the right, the function is approaching to this value here, which looks like 3. Okay, and then when x approaches to 6 from left, so when x approaches to 6 from left, the function is approaching to this value, which is 3. So here, as x approaches 6 from left and right, both values are same. That means limit of h of x as x approaches 6 equals 3. It exists and is 3. Now let's look at one more example here. So now next we are going to take -3, which is right here. Okay, so here is -3. So when x approaches -3 from right, so when x approaches -3 from right, we clearly see that the function is approaching to this value here, and the y value here is 0. Now, when x approaches -3 from the left, so when x approaches -3 from the left, the function, okay, the function is approaching to this value, which is 1. Now the right hand limit is 0, the left hand limit is 1. That means limit of h of x as x approaches -3 does not exist. So this limit does not exist. So again, you can pause the video and then try this example and you can check your work. So let's look at the first one. As x approaches 4 from the right here, the function is approaching to this value, which is 1. Now, as x approaches 4 from the left, so when you go to 4 from the left, the function is approaching to this value right here, which is 2. Here, the right hand limit is not same as left hand limit, so this limit does not exist. We just write DNE, which means does not exist. Now, similarly, let's look at the second one here. As x approaches 2 from the right, so as x approaches 2 from the right, the function is approaching to this y value here. It's on the x-axis, so the y value is 0. Now, when x approaches 2 from the left, so we are approaching to 2 from the left, the function is approaching to this y value, which is again 0. That means the left hand limit is same as right hand limit. So the limit of f of x as x approaches 2 is 0. Now similarly, limit when limit of f of x as x approaches -4 from the right. So this is -4 right here. So when x approaches -4 from the right, this is the graph going from the right. So the y value or the function is approaching to this value, which is 6. Now when x approaches to -4 from the left, so when you move towards 4 from the left, on the graph you're moving this way towards that point, which is -4. That means the left hand limit is not same as right hand limit, so this limit does not exist. I think with these two examples, you have clear idea about how to find limit from the graph. Okay. Now the next one, we are going to look at finding the limit of a function when you are given a function and then using a table. So for that, we do the same thing that we did at the beginning of this section. We'll make a table from left and right. So we'll take x values close to that a value from left and right and see where the function is heading to. Okay, so let's go ahead and make this table. So let's say this one, x is approaching to 9 from the left. Okay, so that means I'm going to take the values of x equals 8.9, 8.99, and then 8.999 and 8.9999. So that means here is 9. So we are approaching to 9 from the left. So I'm taking these values. Okay. Now if I take this value and plug it in here in the function, so it is x minus 9. So 8.9 minus 9 divided by square root of 8.9 minus 3. So if we put this into the calculator, so I took the first value and put it into the function. So this is the function here, okay? And then if you put that into the calculator, we'll get 5.98328. So this means 5.98328. Okay, so similarly, let's plug in other values into the calculator and then see what we get. Okay, so I'm not going to show all the work here. You can put it into the calculator and then you can find the values. So when we plug in 8.99, we are going to get 5.99833. When we plug in 8.999, we get 5.99983, and there are more numbers. Okay, I'm just writing few decimal places. Then if we plug in 8.999, then we get 5.99998, and then more numbers after that. It looks like this when we take x very close to 9, when we're approaching to 9, these values are looks like they're approaching to 6. Okay, now let's do the same thing when x approaches 9 from the right. So here is 9, then I'm taking the x values closer to 9 from the right. Okay, so that means I'll take 9.1. Okay, then I'll take 9.01, and then I'll take 9.001, then I'll take 9.0001, which is very close to 9. So again, if we put this into the calculator, this is what we are going to get. So 6.01662, and then for 9.01, we'll get 6.00166, and then we get, when we plug in 9.001, we get 6.000166, and then there are more numbers after that. Okay, so when we plug in 9.00001, we are going to get 6.0000166. So again, from here we see the same pattern. These numbers are approaching to 6. So from both the directions, the numbers are approaching to 6. Now, if you go ahead and graph this function in your calculator, this is how the graph looks like. Okay, so the graph of this function looks like this. That means when x approaches 9, okay, when x approaches 9 from left and right, the function is approaching to this value right here, which is 6. Okay, though the function is undefined at x equals 9, but we see that from both directions the function is approaching to the same point or same value, which is 6. So from the graph and table, so from the graph and the table, we can say that limit x approaches 9 of x minus 9 over square root of x minus 3 equals 6. That means as x approaches 9 from both the direction, the value of this function given here is approaching to 6. Let's look at another function here. So next we are going to look at sine of x over x. So again, we are going to take some values. So let's say x approaches 0 from the left. So this is 0, but we are going to take numbers close to 0 from the left. That means we are going to take negative numbers. So let's go ahead and take negative 0.1, and then negative 0.01, then negative 0.001, then negative 0.0001. Okay, so when you're putting this into the calculator, make sure that your calculator is in radian mode. If it's in degree, make sure that you switch that to radian mode. Okay, so now if you put this into your calculator, so you just have to do sine of negative 0.1 divided by negative 0.1. Okay, so if you put that into the calculator, so this is what we are going to get. So we get 0.998334166, and there are more numbers after that. I'm not going to write all of them. So if you plug in negative 0.01, then you will get 0.999983, and then more numbers after that. Now, when we plug in negative 0.001, we get 0.9999969, okay, and then 83, and then more numbers after that. Similarly, when we plug in negative 0.001, we'll get 0.9999999. There are 8 nines, so 1 2 3 4 5 6 7 8 nines, and then we get 83, and then more numbers after that. So it looks like clearly from here we see that as x approaches 0 from the left, the value of this function is approaching to 1. So let's leave that there, and then let's take some values from the right. We can take the same values from the right. Let's take the positive value. So we take 0.1 and we move closer, which is 0.01, and then 0.001, and then 0.0001, which is very close to 0. Now, the good thing here is if you plug this into your calculator, you are going to get exact same value that you have for the negative, and you can verify that putting into your calculator. I already have the values here, so I'm going to write it. So for 0.1, you are going to get 0.998334166, and more numbers after that. So when you plug in 0.01, you are going to get 0.9999, and then 8 3 and more numbers. When you plug in this one, you are going to get 0.99999983 and more numbers, and then same thing here, you're going to get 0.999999983 and more numbers. So clearly we see that this is also approaching to 1. That means from both direction, as x approaches 0, the value of the function is approaching to 0. And then if you grab this function again at 0, the function is undefined. We have a hole here, but from both directions, we clearly see that the function is approaching to 1. So that means from the graph and the table, we can write limit as x approaches 0, sine of x over x equals 1. Now you can pause the video and try this example, okay? Make the table, do the same thing that we did for the previous example, and then you can resume the video and check your work. So what we're going to do here is, let's take x approaches 0 from the left, and then in this table, we are going to take x approaches 0 from the right, okay? So we'll take the same values that we took for the previous function. So we're going to take negative 0.1, then negative 0.01, then negative 0.001, and then negative 0.0001, okay? So do the same thing. So you can take cosine 1 over negative 0.1 and then put it into the calculator, okay? And then do same thing for all the values. I'm going to write the values. So for this one, we are going to get negative 0.8390715. Then more decimal places after that. I'm not going to write all of them, okay? So the next one, I'm going to get positive 0.86232. Then I get positive 0.562379, and then I'm going to get negative 0.952155. So it looks like we are not approaching to any particular value here. So we have a negative number, then we have two positive numbers, then we have a negative number. Then if you keep taking next one, you might get positive, negative, positive, negative, okay? So it looks like we cannot make any conclusion from here, okay? Then let's do the same thing. Let's take the positive value and check what we get. Okay, so if you take x equals 0.1, we'll get negative 0.8390715. We get the same value that we have here, okay? So if you take 0.01, then we get 0.86, so we'll get positive value, and then more numbers after that. 0.001, 0.562379, and then more numbers after that. So 0.0001, we get negative 0.952155, and then more numbers. So we get the same value from the both sides, but they are not approaching to the to some particular value like the one in the previous example. If you look at the previous example, we see that pattern that this is approaching to 1. All these numbers are approaching to 1. But if you look over here, we have a negative number. So in the graph, if you look at it, or in the number line, so you see you have a negative value, then you have a positive value, then you have another negative value, then it's not approaching to the same value or a particular value. So now let's check that with the graph. So if you go ahead and graph this function in your calculator, this is how the graph looks like. And clearly, if you see here, as x approaches 0, okay, so as x approaches 0, the graph of the function oscillates, okay, so it goes to negative, positive, negative, positive, negative, positive. So it keeps oscillating. That means it's not approaching to a particular value here. So that means if a function is not approaching to a single point, a single value from both direction, then the limit does not exist. So we'll say that limit as x approaches 0 of cosine of 1 over x does not exist. Now we'll just do this much for this video. In the next video, what we are going to do is, so in this video, we looked at finding limits from graphs and tables, but this is, I think, too much work, right? So we have to make this table, and then we have to look at the graph, and then make estimation. It's not going to give us exact value. We just have to look at the number pattern and make estimation or the approximation. So this is not really a good idea to calculate limit. It's a good idea to understand the limit, but it's not really a good idea to calculate the limit. So what we are going to do is, in the next section, we'll learn some techniques that helps us to find the limit algebraically. So we don't have to make a table, or we don't have to look at a graph. We can do some algebra, and then we can find the exact limit without making tables and graph, or without doing any approximation or estimation. So that's what we'll see in the next video. We'll just stop this video right here.